Throughout most of human existence, people saw the Andromeda Galaxy as just a dim blur in the darkness above. Many believed it was a nebula, simply a patch of gas floating within the Milky Way. Some people imagined something grander, thinking it could be a completely separate galaxy. When scientists finally learned the truth, it changed how we understood our universe. Andromeda isn't simply another object in space. It stands as the biggest galaxy in our local neighborhood, containing 1 trillion stars and countless unknowns. The Milky Way and Andromeda are heading toward each other, eventually merging to form something completely different. If you like the content, consider liking and subscribing to the channel. Today, we will find out, what mysteries does this neighboring galaxy contain? Might it have planets we haven't yet found? Could humans or our creations someday cross the space between galaxies to get there? Get ready as we begin. Part 1. The Great Debate: Nebula or Galaxy? During the early 1900s, scientists struggled with a question that would transform our view of the universe. Was the Andromeda Nebula simply another gas cloud inside the Milky Way? Or was it a completely separate galaxy similar to ours, but incredibly distant? Back then, people thought the universe was much smaller. Most researchers assumed the Milky Way held everything: all stars, all planets, and all gas clouds. When telescopes showed faint glowing spots in the night sky, scientists classified them as nebulae, thinking they were clouds of material between stars, possibly creating new stars. Andromeda was one of these puzzling objects, a spiral-shaped light patch that stood out among the many other nebulae recorded in the sky. The argument over Andromeda's real nature grew stronger in the early 1900s. Some scientists claimed it was a separate star system, its own island universe. This represented a revolutionary concept. If Andromeda was indeed a galaxy, the universe was much larger than anyone had thought. This would mean the Milky Way wasn't alone, but was one of many galaxies spread throughout space. One of the main arguments against Andromeda being a separate galaxy was the assumption that the Milky Way was large enough to include everything. In 1917, scientist Harlow Shapley calculated the Milky Way's size and determined it measured about 300,000 light-years in diameter, which seemed enormous at the time. If Andromeda existed outside the Milky Way, it would need to be millions of light-years distant, a distance that seemed nearly impossible to believe. Shapley and those who agreed with him thought all known nebulae belonged to our galaxy and that the concept of other galaxies was pointless. Heber Curtis, another respected scientist, disagreed with this view. He pointed to specific observations suggesting Andromeda might lie far beyond the Milky Way. One major hint was the appearance of novae, exploding stars that briefly shine very brightly before dimming. Curtis discovered that novae in Andromeda looked much dimmer than those seen in the Milky Way. If these were truly the same kind of events, the only reason would be that Andromeda sat much farther away than previously believed. Curtis also examined Andromeda's structure itself. It showed a spiral shape similar to other mysterious spiral nebulae visible in the sky. If these spirals were just gas clouds within the Milky Way, it remained unclear why they had such distinctive organized structures. However, if they were separate galaxies, their spiral shapes made better sense. They were huge collections of stars similar to the Milky Way itself. This scientific disagreement reached its peak in 1920 at a famous meeting called the Great Debate. Shapley and Curtis publicly presented their positions at the Smithsonian Institution, each showing their evidence for and against the concept that Andromeda was a separate galaxy. Shapley defended the idea of a single galaxy universe, arguing that the Milky Way was so enormous that considering other galaxies was unnecessary. Curtis, however, maintained that Andromeda and other spiral nebulae were independent star systems. The debate ended without a clear winner. Both men presented convincing arguments, and no definitive proof existed to resolve the question. Nevertheless, the search for answers continued. Within just a few years, the mystery surrounding Andromeda would finally be solved. Part 2. Hubble's groundbreaking discovery. In 1924, Edwin Hubble made a revolutionary discovery using the 100-inch telescope at Mount Wilson Observatory in California. Central to Hubble's work was a type of star called a Cepheid variable. These stars pulse in a steady rhythm, becoming brighter and dimmer over time. Earlier in the century, scientist Henrietta Swan Leavitt had studied Cepheids and found a crucial relationship. The longer a Cepheid's pulsation cycle, the brighter it actually is. This meant that if scientists could measure how quickly a Cepheid changed in brightness, they could figure out its true brightness. Comparing this with how bright it looked from Earth allowed them to calculate its distance. When Hubble calculated Andromeda's distance, the result was shocking. It was over 2 million light-years away. This placed Andromeda far outside the Milky Way's boundaries, proving definitively that it was a separate galaxy. Hubble's discovery transformed astronomy immediately. The Milky Way was no longer the entire universe. It was just one of many galaxies, each holding billions of stars. The argument that had continued for decades was finally resolved. The concept of an island universe was no longer just a theory. It had become reality. This revelation opened doors to even greater discoveries. As telescopes improved, scientists found more and more galaxies stretching across the universe, some much bigger than the Milky Way. The understanding that our galaxy was just one of many led to new questions about the universe's size, structure, and beginnings. The field of cosmology expanded quickly, moving beyond simply studying the Milky Way to exploring the universe as a whole. Even after Edwin Hubble's discoveries changed astronomy, doubts and unanswered questions remained. Science rarely progresses in a straight path, and the confirmation that Andromeda was a galaxy didn't eliminate all uncertainty. Some scientists hesitated to fully accept the new model of the universe, and certain early observations seemed inconsistent with the idea of multiple galaxies. One of the biggest continuing concerns involved how bright galaxies appeared. If they actually sat millions of light-years away, their true brightness had to be far greater than anyone expected. Some researchers found it hard to believe that individual galaxies could shine so brightly across such enormous distances. It was challenging to explain how these massive structures generated so much light, especially when scientists still didn't fully understand the energy processes inside stars. At that time, the main theory about how stars produced energy was still being debated. The idea that stars relied on nuclear fusion to maintain themselves wasn't yet fully established. In the early 1900s, many researchers still thought stars might shine due to gravitational contraction, slowly compressing under their own weight to create heat. However, this process couldn't explain how stars kept their brightness for billions of years. If galaxies held billions of stars, as Hubble's work indicated, then a new understanding of stellar energy production was needed to account for the amount of light released. This issue wasn't resolved until the mid-20th century, when scientists confirmed that stars were powered by nuclear fusion, converting hydrogen into helium in a process that released vast amounts of energy. There were also questions about how galaxies were distributed. If the universe contained countless galaxies, why did they seem concentrated in certain areas while other regions appeared nearly empty? Some sky surveys showed clustering patterns that didn't immediately make sense. Early observations suggested galaxies weren't scattered randomly, but instead seemed to form groups and clusters. Some scientists wondered whether this was an illusion caused by telescope limitations, while others suspected it was a basic feature of how galaxies were arranged. If galaxies were forming groups, what force caused this? Gravity seemed like the obvious explanation, but researchers didn't yet have the tools to fully study the large-scale movements of galaxies. Another source of doubt came from early attempts to measure galaxy movement. Hubble had shown that galaxies were moving away from us, but some scientists found odd exceptions. A few galaxies appeared to have very little redshift, suggesting they weren't moving away as quickly as others. Even more strangely, Andromeda itself seemed to be moving toward the Milky Way, not away. If the universe was expanding, why was this massive galaxy on a collision path with ours? The explanation, as researchers later understood, was that the overall expansion of the universe didn't prevent nearby galaxies from having their own movements due to gravity. Andromeda and the Milky Way were close enough that their mutual gravitational attraction dominated over cosmic expansion, pulling them together. Part 3. Understanding Andromeda's composition. Andromeda, also called Messier 31 or M31, eventually became one of the most studied galaxies in the universe. As scientists moved past the question of whether it was a galaxy, they focused on understanding its structure, composition, and hidden complexities. What they discovered was a vast system filled with billions of stars, swirling gas clouds, mysterious halos of dark matter, and a history of galactic mergers that shaped it over billions of years. Like the Milky Way, Andromeda contains stars of all ages, from young blue giants to ancient red dwarfs that have burned for billions of years. In its bright central region, older red stars dominate, suggesting a long history of stellar development. These stars formed early in the galaxy's life, using up much of the available gas. But in its spiral arms, where dense clouds of gas and dust still remain, younger stars are constantly being born. These regions glow with the light of hot blue stars that formed relatively recently in astronomical terms. A galaxy filled only with old stars would suggest it had stopped creating new ones long ago, while a galaxy packed with young stars would imply it was still in early development stages. Andromeda, however, is a mixture of both, meaning it has gone through cycles of star formation, sometimes creating bursts of new stars while at other times remaining quiet. These cycles are driven by the movement and interaction of gas, which serves as the raw material for new stars. Andromeda's vast reserves of gas and dust provide clues about how the galaxy continues to evolve. Hydrogen, the most common element in the universe, makes up much of the gas within the galaxy. Large hydrogen clouds float between the stars, sometimes gathering into dense regions where gravity pulls the material together. If enough gas collects in one place, the pressure and temperature rise until nuclear fusion ignites, forming a new star. In some regions, entire clusters of stars are born from a single massive gas cloud. Some of the gas doesn't match the movement of the rest of the galaxy, suggesting that Andromeda has absorbed smaller galaxies over time. When a small galaxy drifts too close, Andromeda's gravity pulls it in, stripping away its stars and gas, adding them to its own structure. These galactic mergers have left behind faint streams of stars and disrupted patterns of gas, signs of past collisions. Surrounding the galaxy is an enormous halo of invisible material that doesn't emit or reflect light. This hidden substance, known as dark matter, is thought to make up most of Andromeda's mass, yet it remains undetectable except through its gravitational effects. Scientists first suspected dark matter's presence when they studied how galaxies rotate. In a typical system, the stars and gas at the edges of a galaxy should orbit more slowly than those near the center, much like how planets in the solar system move slower the farther they are from the sun. but observations showed that Andromeda's outer stars were moving just as fast as those closer to the core. The only explanation was that some unseen mass was providing extra gravity, holding the stars in place. By studying the motion of stars and gas, researchers estimated that Andromeda contains far more dark matter than normal matter. The visible stars, gas, and dust account for only a fraction of the galaxy's total mass. The rest is locked away in this invisible component, forming a massive halo that stretches far beyond the galaxy's main disk. This dark matter is thought to form a kind of cosmic framework, shaping the growth and evolution of galaxies. But despite decades of research, its exact nature remains unknown. Andromeda's structure also includes a bright central bulge, a thick disk of stars, and extended spiral arms. The core of the galaxy is densely packed with older stars surrounding a supermassive black hole at the center. This black hole is millions of times the mass of the Sun, though it appears to be less active than some found in other galaxies. It doesn't consume large amounts of material, meaning it doesn't produce the powerful jets and radiation seen in more energetic galaxies. Moving outward from the core, the thick disk of stars extends across a massive region, with spiral arms curving outward in a familiar pattern. These arms aren't solid structures, but instead consist of waves of density that move through the galaxy, triggering star formation as they pass through clouds of gas. Over time, these arms shift and change, influenced by the gravitational pull of Andromeda's many smaller satellite galaxies. Andromeda is surrounded by dozens of smaller galaxies that orbit it like moons around a planet. These include dwarf galaxies such as M32 and M110, which are gradually being torn apart by Andromeda's gravity. Some of these smaller galaxies may eventually merge completely, adding their stars and gas to Andromeda's growing structure. The galaxy is also home to a vast population of globular clusters, dense groups of tightly packed stars that orbit around the central region. These clusters contain some of the oldest stars in Andromeda, remnants from its earliest days. Studying these clusters provides insight into how galaxies form and evolve over time, as they serve as ancient records of the conditions that existed billions of years ago. Recent studies of Andromeda have revealed even more unexpected features. Scientists discovered a vast, thin plane of dwarf galaxies orbiting the main galaxy in a coordinated pattern, a structure that challenges current theories of how galaxies form. The reason for this alignment is still unclear, as simulations suggest that satellite galaxies should be randomly distributed rather than arranged in a flat plane. Another surprising find is the discovery that Andromeda has experienced at least one major merger in its past. While the Milky Way has grown mostly by absorbing smaller galaxies, Andromeda appears to have collided with a larger system at some point in its history. This ancient merger reshaped the galaxy's structure, scattering stars and gas across vast distances. The evidence for this event comes from the motion of stars in Andromeda's outer halo, where remnants of a past galaxy still linger. As the closest large galaxy to the Milky Way, Andromeda serves as a cosmic laboratory for understanding how galaxies work. Researchers are still working to determine how its supermassive black hole affects the surrounding stars, and how its satellite galaxies interact with its larger structure. New telescopes and instruments will provide even deeper insights, allowing scientists to map the galaxy in greater detail than ever before. Just as a forensic scientist studies traces of material at a crime scene, scientists examine the light from Andromeda to determine what elements make up its stars, gas, and dust. This chemical fingerprint is unique, shaped by billions of years of stellar evolution, collisions, and cosmic recycling. The most common element in Andromeda, as in the rest of the universe, is hydrogen. It's the simplest and most abundant element, forming the primary fuel for star formation. Alongside hydrogen, helium is also present in large amounts, produced in the early moments of the universe during the Big Bang. These two elements form the building blocks of stars. But what makes Andromeda chemically unique is the heavier elements that have been created within its stars over billions of years. As stars go through their life cycles, they create new elements through nuclear fusion. Lighter elements such as carbon, nitrogen, and oxygen are formed in smaller stars, while heavier elements like iron, nickel, and gold emerge in more massive stars and explosive supernova events. These newly formed elements are released into space when stars die, mixing into the surrounding gas and dust. This cycle continues as new generations of stars form from enriched material, each one containing a slightly different chemical makeup than the last. The chemical diversity in Andromeda isn't uniform. The oldest stars in the galaxy's halo, which formed billions of years ago, contain fewer heavy elements compared to the younger stars found in the spiral arms. This is because these early stars formed before many of the heavier elements had a chance to accumulate. In contrast, the spiral arms, where new stars continue to form, are rich in metals. Scientists refer to all elements heavier than helium as metals, indicating that they have been enriched by multiple generations of stellar activity. One of the most striking chemical features of Andromeda is the presence of unusual isotopic ratios. Isotopes are different forms of the same element, containing the same number of protons, but varying numbers of neutrons. Certain isotopes, such as those of oxygen and carbon, provide valuable clues about the processes that have shaped the galaxy. Researchers have found differences in these isotopic ratios when comparing Andromeda to the Milky Way, suggesting that the two galaxies have had different evolutionary paths. These variations can be traced back to the types of stars that contributed to Andromeda's chemical makeup. Some isotopes are produced in the intense heat of massive stars, while others are formed in slower-burning, smaller stars. By analysing the distribution of these isotopes, scientists can determine which kinds of stars played a dominant role in shaping Andromeda's composition. The patterns they've observed suggest that Andromeda has experienced a different rate of star formation and possibly different kinds of stellar explosions compared to the Milky Way. When a galaxy merges with another, it not only absorbs stars, but also gains any unusual chemical signatures carried by the incoming system. Some of Andromeda's outer regions show signs of elements that don't match the typical composition of its main disk. These could be remnants of long-lost galaxies that were absorbed by Andromeda, leaving behind traces of their unique chemical identities. The core of the galaxy contains a higher concentration of iron and other heavy elements compared to the surrounding areas. This suggests that Andromeda's core may have undergone intense periods of star formation and supernova activity in the past. Some of these elements could have been created in short-lived massive stars that exploded violently, enriching the surrounding space with heavier elements. This process is similar to what has been observed in other galaxies with active star-forming regions. Dust grains, composed of tiny solid particles of carbon, silicon, and other elements, are scattered throughout the galaxy. These dust particles play an important role in the formation of new stars and planets, as they provide the raw materials needed to build planetary systems. The chemical composition of this dust varies across the galaxy, with some regions containing more carbon-rich grains, while others are dominated by silicates similar to the rocky materials found on Earth. One of the key tools scientists use to analyze Andromeda's chemical fingerprints is spectroscopy. By studying the light emitted or absorbed by different elements, researchers can determine the precise composition of the galaxy. This technique has revealed the presence of molecules such as carbon monoxide, which is often found in dense clouds where new stars are forming. The detection of these molecules helps scientists understand how Andromeda continues to evolve and produce new generations, of stars. As the galaxy continues to form stars, its overall metallicity, the abundance of elements heavier than helium, will increase. However, as its supply of raw gas slowly depletes, the rate of star formation will decline. Eventually, Andromeda will become a galaxy dominated by older stars with fewer new ones being born. When it eventually merges with the Milky Way in about 4 billion years, the combined galaxy will carry the chemical fingerprints of both systems, blending their histories into a new cosmic identity. Part 4. Rare and unusual stars. Andromeda is home to an immense variety of stars, many of which follow predictable life cycles and match what scientists see in other galaxies. However, scattered among these common stars are some rare and unusual types. Some of them are remnants of violent cosmic events, while others are still forming in ways that challenge current models of stellar birth. One of the most intriguing groups of rare stars in Andromeda is the population of luminous blue variables. These stars are massive, unstable, and prone to sudden changes in brightness. They exist in a delicate balance between gravity and radiation pressure, with their outer layers frequently being blown away by strong stellar winds. One of the best-known examples of a luminous blue variable in Andromeda is AE Andromedae, which has been observed to fluctuate in brightness over time. These stars are thought to be in a short-lived phase of evolution before they explode as supernovae, making them key targets for understanding the final stages of massive stars. Scattered throughout Andromeda's spiral arms are a number of Wolf-Rayet stars, a rare and extreme category of hot massive stars nearing the end of their lives. These stars have already lost most of their outer hydrogen layers, exposing the deeper, hotter regions where heavier elements are being formed. Because of this, Wolf-Rayet stars emit strong stellar winds and shine with an intense blue-white light. Their presence indicates regions of recent star formation, as they only live for a few million years before collapsing in dramatic supernova explosions. Then there are Andromeda's hypervelocity stars, stars moving at extraordinary speeds that shouldn't be possible under normal conditions. Some of these stars may have been ejected from binary systems when their companion exploded as a supernova. Others could have been flung outward after a close encounter with Andromeda's supermassive black hole. These hypervelocity stars travel so fast that some may eventually leave the galaxy entirely, carrying with them clues about the extreme gravitational forces at play within Andromeda. In the outer reaches of the galaxy, a different kind of rare star lurks: carbon stars. These stars have an unusual abundance of carbon in their atmospheres, which gives them a distinctive reddish glow. Carbon stars are thought to form when convection within the star dredges up carbon from deeper layers, enriching the outer atmosphere. This process changes the way the star emits light, making it appear redder than normal. Andromeda's carbon stars are particularly interesting because they hint at how chemical elements are recycled in galaxies over time. These stars shed carbon-rich material into space, helping to enrich the interstellar medium with the raw materials needed for future star and planet formation. Deep in Andromeda's central bulge, scientists have found an unusual population of extremely metal-poor stars. Stars that formed in the early history of the galaxy when heavier elements were still scarce. These stars are relics from a time when the universe was much younger, and their compositions provide a glimpse into what conditions were like billions of years ago. Because they contain so few heavy elements, they're believed to be some of the oldest stars in Andromeda, possibly dating back to the time when the galaxy was just beginning to take shape. Yellow supergiants are stars that are caught in a brief transition phase between being red supergiants and blue supergiants, making them difficult to observe. Yellow supergiants are rare because their evolutionary phase lasts only a few thousand years, a mere blink of an eye in cosmic terms. Their presence in Andromeda provides important data about the life cycles of massive stars, as they can help scientists refine their models of how these stars change over time. Perhaps one of the strangest categories of stars in Andromeda are magnetars, neutron stars with incredibly powerful magnetic fields. These remnants of collapsed massive stars emit bursts of high-energy radiation and have magnetic fields trillions of times stronger than Earth's. The detection of magnetars in Andromeda suggests that the galaxy has experienced a significant number of supernova explosions, each of which could have left behind one of these highly magnetized remnants. The study of these objects helps researchers understand extreme physics in ways that cannot be replicated in laboratories on Earth. Variable white dwarfs are tiny but dense remnants of dead stars that sometimes show unexpected variations in brightness, which can be caused by pulsations or interactions with surrounding material. Unlike more common white dwarfs, these rare versions may be part of binary systems where they're slowly pulling material from a companion star. In some cases, this process can lead to a sudden thermonuclear explosion known as a nova, temporarily making the white dwarf thousands of times brighter before it fades back into obscurity. Each new observation adds to the growing understanding of how stars evolve, how galaxies change over time, and how different cosmic environments influence the life cycles of stars. These hidden luminaries, often overlooked in broader discussions of galaxies, provide essential clues about Andromeda's past and its future, showing that even within a well-studied galaxy, there are still mysteries waiting to be uncovered. Andromeda isn't just a collection of isolated stars, but a vast cosmic landscape where stars gather in clusters, forming communities that evolve together. Some of these clusters are dense and ancient, while others are loosely bound and relatively young. One of the most striking types of clusters found in Andromeda is the population of globular clusters. These dense spherical groupings of stars are among the oldest structures in any galaxy, often containing stars that formed early in cosmic history. Andromeda has far more globular clusters than the Milky Way, with estimates suggesting over 500 of them orbiting the galaxy. Some of these clusters, however, appear different from those typically seen in other galaxies. A few contain stars that are significantly younger than expected, raising questions about how they formed. Others seem to have unusual motions, suggesting they may not have originally belonged to Andromeda, but were captured from smaller galaxies during past collisions. Scientists have also identified a surprising number of extended clusters in Andromeda, groups of stars that aren't as densely packed as traditional globular clusters, but still remain gravitationally bound. These clusters are unusual because they blur the line between star clusters and small galaxies. Unlike typical globular clusters, which are tightly bound and relatively spherical, extended clusters have more spread out structures and lower overall densities. Some researchers believe these objects could represent a transitional phase between clusters and dwarf galaxies, offering a rare glimpse into how galactic structures evolve over time. A particularly mysterious type of star cluster in Andromeda is the so-called faint fuzzy cluster. These clusters were first identified in Andromeda's outer regions and appear to be distinct from both globular clusters and open clusters. They contain old stars similar to globular clusters, but are more loosely structured, making them less likely to survive for billions of years without being disrupted by gravitational forces. Some theories suggest they might have originated in a long-ago merger between Andromeda and a smaller galaxy, leaving behind remnants that have slowly dispersed over time. Andromeda also hosts an unexpected number of young, massive clusters. These contain bright, hot stars that are only a few million years old. The presence of these young clusters is surprising because many of them are found in regions where star formation was thought to have largely ceased. Some of these clusters are located far from Andromeda's main star-forming regions, leading to speculation that they may have been formed by tidal interactions or triggered by past collisions with satellite galaxies. There are star clusters that don't match the chemistry of the rest of the galaxy. Some of these contain stars with unusual metal ratios. A few clusters even appear to have compositions more similar to those found in dwarf galaxies rather than in a large spiral galaxy like Andromeda. This suggests that Andromeda has been absorbing smaller galaxies over time, with their star clusters becoming part of its stellar population. Studying these clusters provides evidence of Andromeda's history of mergers and acquisitions, allowing scientists to reconstruct past events that shaped the galaxy into what it is today. Part 5. Black holes in Andromeda. At the heart of Andromeda lies one of its most powerful features, a supermassive black hole. This immense object, hidden deep within the galaxy's core, influences everything around it, shaping the motion of stars, bending light, and consuming matter that strays too close. Researchers have long suspected that most large galaxies harbour such black holes at their centres. Observations reveal that Andromeda's supermassive black hole, called M31, is about 140 million times the mass of the Sun, making it significantly more massive than the Milky Way's central black hole, Sagittarius A. The presence of such a massive object at Andromeda's core raises questions about how it formed and grew to its current size. Some theories suggest that as Andromeda was absorbing smaller galaxies over billions of years, each brought its own black hole. These black holes merged, creating a single larger one at the galaxy's centre. Surrounding M31 is a dense, compact cluster of stars, an unusual feature that sets it apart from other galactic centres. These stars move at incredible speeds, pulled by the immense gravitational force of the black hole. Observing these motions helped scientists confirm the black hole's existence, as only such an extreme concentration of mass could account for the way these stars behave. Unlike some other galaxies, M31 doesn't currently appear to be consuming large amounts of matter. Many black holes at the centres of galaxies form what's known as an active galactic nucleus, where gas and dust swirl around them, heating up and producing powerful radiation. Andromeda's black hole, however, is relatively quiet, emitting only small amounts of X-ray and radio waves. Researchers believe this may be a temporary phase. It's possible that in the past, the black hole was more active, pulling in material and releasing energy that could have shaped Andromeda's core. Future collisions with gas clouds or even entire star systems could awaken it again, turning it into a more active and energetic feature of the galaxy. Beyond the central black hole, Andromeda may also contain smaller intermediate mass black holes scattered throughout its structure. These black holes, ranging from hundreds to thousands of times the mass of the Sun, are thought to form from collapsing massive stars or by merging smaller black holes. While supermassive black holes dominate galactic centers, intermediate black holes remain difficult to detect and are among the most elusive objects in astronomy. Some of these smaller black holes may reside in the dense star clusters orbiting Andromeda. There's growing evidence that certain globular clusters may harbor black holes at their centers, influencing the movement of surrounding stars. Wandering black holes don't remain in fixed locations, but drift through the galaxy. These black holes may have formed from past galactic collisions, ejected from their original positions by powerful gravitational forces. Some could be the remnants of smaller galaxies that Andromeda consumed in the past. Black holes are extremely difficult to detect unless they interact with nearby matter. However, their gravitational influence can sometimes be observed when they pass in front of a distant star, momentarily bending and magnifying its light in a process known as gravitational lensing. These objects, though invisible to the eye, exert powerful gravitational forces that can affect star formation, disrupt planetary systems, and even alter the paths of entire star clusters. If Andromeda contains a large number of these hidden black holes, they could play a significant role in its evolution. Gravitational wave detectors, which sense ripples in space-time caused by merging black holes, may also help identify hidden black holes within Andromeda. As technology improves, scientists will be able to explore these enigmatic objects in greater detail, uncovering more about their origins and impact on the galaxy. Part 6. Dark Matter's Role. Without dark matter, Andromeda, along with the Milky Way and countless other galaxies, wouldn't exist in its current form. One of the first clues to dark matter's presence in Andromeda came from the way the galaxy rotates. If Andromeda consisted only of the stars, gas, and dust that scientists can see, then the outer regions of the galaxy should be moving much more slowly than the inner parts. The simplest explanation is that Andromeda is surrounded by an enormous halo of unseen material, stretching far beyond the visible edge of the galaxy and outweighing all the stars and gas combined. The sheer amount of mass needed to explain Andromeda's motion suggests that dark matter makes up most of the galaxy's total mass. If the stars, planets, and gas clouds that make up Andromeda were all that existed, their combined gravity wouldn't be enough to keep the galaxy bound together. The distribution of dark matter in Andromeda isn't uniform. Some regions appear to have higher concentrations than others. Researchers have mapped dark matter through gravitational lensing. By studying the way light curves as it passes through different parts of Andromeda's halo, scientists can piece together an image of this invisible material. These studies suggest that dark matter isn't completely smooth, but instead has a clumpy structure, possibly shaped by interactions with smaller satellite galaxies or by the gravitational forces at play within Andromeda itself. The influence of dark matter plays a crucial role in how Andromeda interacts with its neighbouring galaxies. Andromeda belongs to the local group, a cluster of galaxies that includes the Milky Way and many smaller ones. The gravitational pull from Andromeda's dark matter halo extends far beyond its visible boundaries, affecting how nearby galaxies move. Some of these smaller galaxies, like the dwarf satellites orbiting Andromeda, are kept in place by dark matter-esque gravity, preventing them from drifting into deep space. Others are slowly being drawn inward, pulled by Andromeda's massive invisible halo. One of the great mysteries about dark matter in Andromeda involves what will occur when it collides with the Milky Way billions of years from now. When that happens, the visible stars and gas clouds of both galaxies will interact dramatically, creating new star clusters and reshaping their structures. However, dark matter will behave very differently. Since it doesn't collide in the same way as ordinary matter, the dark matter halos of both galaxies will pass through one another. Their immense gravitational fields will merge, reshaping the structure of the resulting supergalaxy. If dark matter is composed of weakly interacting particles, as many scientists believe, the way it redistributes after the collision could reveal important clues about its nature. But if dark matter can interact with itself in some way, the merger could produce strange and unexpected effects in the combined galaxy. A deeper question still lingers: did dark matter form along with galaxies like Andromeda? Or was it already present long before stars began to shine? Some theories propose that dark matter particles were created right after the Big Bang, spreading throughout the universe and forming the invisible framework upon which galaxies later developed. Others suggest it may be linked to unknown forces or undiscovered particles. Scientists hope that by mapping dark matter more precisely and studying its effects on Andromeda's stars, they can eventually solve one of the greatest mysteries of modern astronomy: the true nature of this unseen yet essential part of the universe. Mapping a galaxy as massive as Andromeda is a monumental task. Even though it's the closest large galaxy to the Milky Way, its enormous size means that it can be captured in a single telescope image. Creating a full view requires stitching together countless smaller photographs, a process that can take years. The Hubble Space Telescope produced one of the most detailed portraits of Andromeda by combining thousands of separate exposures, revealing millions of stars across its vast expanse. But mapping Andromeda isn't just about pictures. It involves measuring distances, studying motion, and analyzing composition. One of the main tools used in this process is spectroscopy, which allows astronomers to determine the chemical makeup, temperature, and motion of stars and gas clouds. This helps them build a complete map showing not only where stars are, but how they move and interact, and how the galaxy has evolved over time. Motion mapping is equally important. Andromeda isn't static, it rotates, shifts, and even pulls in nearby galaxies. To study this movement, scientists use the Doppler effect, which measures how light wavelengths change as objects move toward or away from us. By studying these shifts across different regions, astronomers can construct a detailed rotation map that shows how various parts of the galaxy spin at different speeds. Interstellar dust complicates things by scattering and absorbing light, hiding many regions from view in visible wavelengths. To see through these dusty areas, astronomers rely on infrared telescopes that can penetrate the clouds and reveal hidden structures. The Spitzer Space Telescope provided a new look at Andromeda by highlighting its dust-filled zones and showing where new stars are forming. Andromeda is also rich in hydrogen gas, which emits a specific wavelength of radio waves detectable even in areas blocked by dust. By mapping these radio emissions, scientists can trace the distribution of gas throughout the galaxy, identifying regions where new stars are likely to appear and how Andromeda replenishes its stellar population. Recent advances in computational modeling have transformed how galaxies are studied. Instead of relying solely on direct observation, astronomers now simulate Andromeda's structure using powerful computers. These models account for star distribution, dark matter influence, and gravitational interactions with other galaxies. By comparing simulations with real data, researchers refine their understanding of how Andromeda formed and continues to evolve. Its smaller satellite galaxies are also carefully studied. Some, like M32 and M110, are bright enough to be seen with small telescopes. M32 is a compact elliptical galaxy filled densely with stars, while M110 is larger and more diffuse, showing signs of past interaction with Andromeda. Both are thought to be remnants of once larger galaxies stripped of their outer layers long ago. Beyond these, many faint dwarf galaxies orbit Andromeda at greater distances. Some, such as NGC 147 and NGC 185, resemble miniature elliptical galaxies with older stars and little new star formation. Others, like IC10, are still forming stars, proof that some have retained their gas despite Andromeda's pull. Initially, scientists assumed these satellites orbited randomly, but observations have revealed a surprising pattern. Many seem to lie along a vast, thin plane rather than being scattered in all directions. This discovery challenges current galaxy formation theories and suggests that these satellites may have formed from a single ancient event. Some researchers even believe that Andromeda's satellite system could be part of a much larger structure, perhaps connected to the Milky Way's own dwarfs, forming part of giant cosmic filaments of dark matter and gas stretching between galaxies. Some of these smaller galaxies are currently being absorbed. As they spiral inward, their stars and gas are pulled into long streams. Observations have found enormous arcs of stars and gas extending from Andromeda remnants of past galactic mergers. One striking example is the giant stellar stream, a ribbon of stars stretching over 100,000 light-years, believed to be the remains of a dwarf galaxy torn apart by Andromeda's S gravity. Its stars, once part of an independent system, are now merging seamlessly into Andromeda's vast halo. Through mapping, modelling and observation, scientists continue to uncover the layers of complexity within Andromeda, its dark matter, its satellites, and its future collision with the Milky Way. Each discovery brings us one step closer to understanding not just this neighbouring galaxy, but the larger story of how cosmic structures form, evolve, and connect across the universe. Dark matter has a powerful effect on how the Andromeda Galaxy interacts with the galaxies around it. Andromeda is part of the local group, a family of galaxies that includes the Milky Way and many smaller companions. The gravitational influence of Andromeda's dark matter halo stretches far beyond what we can see, shaping the motion of nearby galaxies. Some smaller ones, such as the dwarf satellites orbiting Andromeda, are held in place by this invisible gravity, keeping them from drifting into deep space. Others are slowly being drawn closer, pulled inward by the galaxy's immense dark matter halo. One of the biggest mysteries about Andromeda's dark matter is what will happen when it eventually collides with the Milky Way a few billion years from now. During that colossal encounter, the stars and gas clouds of both galaxies will interact violently, creating new star clusters and reshaping their forms. Yet dark matter will act very differently. Because it doesn't collide or interact like normal matter, the dark matter halos of both galaxies will pass through one another. Their gravitational pull, however, will combine and mold the structure of the new merged galaxy. If dark matter consists of weakly interacting particles, as many scientists propose, its behavior after the collision could provide important clues about its true nature. But if dark matter can interact with itself in some unknown way, the outcome could reveal strange, unexpected patterns in the merged system. A deeper question remains: did dark matter form alongside galaxies like Andromeda? Or did it already exist in the early universe, long before the first stars appeared? Some theories suggest that dark matter particles were created right after the Big Bang, spreading across the cosmos and forming the invisible framework that allowed galaxies to take shape. Other ideas link it to forces or particles that scientists have not yet discovered. By carefully mapping dark matter and observing how it affects Andromeda's stars, astronomers hope to uncover the secrets of this hidden but vital part of the universe. Mapping a galaxy as enormous as Andromeda is a massive challenge. Although it's the closest large galaxy to the Milky Way, it's still so vast that no single telescope image can capture it completely. To create a full picture, astronomers must piece together thousands of smaller images, a process that takes years. The Hubble Space Telescope achieved one of the most detailed views of Andromeda by merging thousands of individual photos, revealing millions of stars scattered across its spiral arms. But mapping isn't just about capturing images, it also involves measuring distances, studying movement, and analysing composition. One of the main tools for this is spectroscopy, which allows scientists to identify the chemical makeup, temperature, and speed of stars and gas clouds. This technique helps create a complete map that shows not only where stars are located, but also how they interact and evolve over time. Tracking motion is another crucial part of understanding Andromeda. The galaxy isn't stationary. It spins, moves, and even pulls smaller galaxies toward itself. To measure these motions, astronomers use the Doppler effect, which tracks how light changes as objects move closer or farther away. By studying these shifts, they can build a detailed rotation map showing how different regions of Andromeda rotate at varying speeds. Interstellar dust adds another layer of difficulty. It blocks and scatters visible light, making some regions nearly impossible to see. To look beyond this dust, scientists use infrared telescopes which can see through the clouds and uncover hidden structures. The Spitzer Space Telescope, for instance, revealed Andromeda S dust-rich regions and pinpointed where new stars are forming. Andromeda also contains massive amounts of hydrogen gas, which emits a distinct radio wavelength detectable even through heavy dust. By mapping these radio signals, scientists can track how gas is distributed across the galaxy, revealing where stars are being born and how the galaxy renews its stellar population. Modern computer simulations have transformed how Andromeda is studied. Astronomers can now model the galaxy S structure in incredible detail, factoring in star placement, dark matter influence, and gravitational interactions with nearby galaxies. Comparing these simulations to real observations allows them to refine theories about how Andromeda formed and evolved over time. Andromeda S smaller companion galaxies are also of great interest. Two of the most noticeable M32 and M110 are visible even with small telescopes. M32 is a compact elliptical galaxy packed with stars, while M110 is larger, more diffuse, and shows signs of past encounters with Andromeda. Both are believed to be the stripped-down remnants of once larger galaxies that Andromeda absorbed long ago. Farther out, many faint dwarf galaxies orbit Andromeda at greater distances. Some, like NGC 147 and NGC 185, resemble miniature ellipticals made up mostly of older stars with little new star formation. Others, like IC10, are still actively forming stars, showing that some have managed to keep their gas despite Andromeda S' gravitational pull. For years, scientists thought these satellite galaxies orbited randomly, but new observations tell a different story. Many seem to align along a vast, thin plane, instead of being scattered evenly in all directions. This surprising pattern challenges existing ideas about galaxy formation, hinting that these satellites might have formed in a single event, rather than being captured separately. Some astronomers even think Andromeda S satellites could be part of a larger structure connected to the Milky Way S-own dwarf galaxies, forming part of vast cosmic filaments made of dark matter and gas stretching between galaxies. Some of these smaller galaxies are currently being absorbed by Andromeda. As they spiral inward, their stars and gas are stretched into long glowing streams. Massive arcs of stars and gas have been observed extending outward remnants of ancient galactic mergers. One of the most striking examples is the giant stellar stream, a ribbon of stars over 100,000 light-years long, believed to be the remains of a dwarf galaxy torn apart by Andromeda S gravity. Its stars, once part of a separate system, are now merging into Andromeda S halo, becoming part of the larger whole. Through careful mapping, detailed modelling, and ongoing observation, astronomers continue to uncover Andromeda S hidden structure, its dark matter, its satellites, and its future collision with our own galaxy. Each discovery brings us closer to understanding not just this nearby cosmic neighbour, but the grand story of how galaxies form, evolve, and connect across the universe. The outer halo of Andromeda, where ancient globular clusters orbit far from the galactic centre, is home to a mix of RR Lyrae stars and other old variable stars. These stars trace the paths of systems that may have once belonged to smaller galaxies, long since absorbed by Andromeda. When viewed as a whole, Andromeda looks like a textbook example of a spiral galaxy, bright core, sweeping arms, and graceful curves. Yet a closer look reveals unusual patterns and anomalies that set it apart from typical spirals, offering clues about its turbulent history and uncertain future. One of the first peculiarities in Andromeda S structure is the existence of two overlapping spiral patterns. Unlike the Milky Way, which has a single dominant set of arms, Andromeda seems to display two spirals that don't fully align. Astronomers believe this double structure could be the result of a past collision, possibly with one of its smaller satellite galaxies. Another oddity is the uneven brightness and density of its spiral arms. In most spiral galaxies, the arms form smooth, continuous curves filled with stars, gas, and dust. But in Andromeda, the arms appear fragmented, some regions packed with young, brilliant stars, while others are thin and faint. This unevenness suggests that gravitational forces, both from within and beyond the galaxy, continue to shape its structure. Beyond its main spiral arms, Andromeda features faint, irregular filaments and smaller outer arms that extend in unexpected directions. These delicate structures, visible only through deep sky imaging, could be remnants of tidal debris left over from ancient mergers or temporary density waves caused by the motion of stars and gas through the galactic disk. Unlike the main spiral arms that remain relatively stable over millions of years, these smaller patterns can shift and evolve over much shorter timescales. A particularly intriguing feature lies in Andromeda's inner disk, ITES, not perfectly symmetrical. One side of the core appears more extended and prominent than the other, giving the galaxy a slightly lopsided shape. For a galaxy of its size, this is highly unusual. Astronomers suspect this asymmetry may have formed when Andromeda interacted with another galaxy, either through a close pass or an ancient merger. The gravitational disturbance from that encounter could have pulled stars and gas into uneven configurations, leaving behind a distorted spiral pattern that still persists today. Some scientists think dark matter could also be responsible for Andromeda's irregularities. As this invisible mass interacts gravitationally with normal matter, it might subtly distort how the spiral arms form and evolve. Typically, in spiral galaxies, new stars form along the leading edges of the arms where gas and dust are compressed. However, in Andromeda, clusters of young, bright stars are scattered outside the main arms, suggesting that other forces like moving interstellar clouds or shock waves from past collisions may play a role in triggering star formation. Unlike the smooth, continuous spirals seen in many galaxies, Andromeda also displays several faint ring-like structures made of stars and gas. These circular formations may be remnants of old collisions, where the impact of a smaller galaxy sent waves rippling outward through Andromeda's disk. Over time, these rings may dissolve and blend back into the spiral pattern, or evolve into new structures entirely. Further out, beyond the visible spiral arms, Andromeda's influence continues in a vast, faint halo. This outer region isn't a smooth continuation of the inner disk, but instead shows irregular, shifting formations. Some of these patterns may be remnants of ancient galactic mergers, while others could result from ongoing gravitational interactions with Andromeda's smaller companions. Despite years of study, this outer region remains one of the least understood aspects of the galaxy, revealing that Andromeda is far more dynamic and complex than the textbook image of a perfect spiral might suggest. Over billions of years, gravity, collisions, and cosmic forces have shaped it into a living, ever-changing system. Beyond Andromeda, as grand structure, lies another frontier, the search for planets in other galaxies. Finding planets beyond our solar system has been one of the most thrilling achievements of modern astronomy. Within the Milky Way, scientists have already confirmed thousands of exoplanets, with many more awaiting discovery. Yet finding planets outside our own galaxy, in galaxies like Andromeda, represents one of astronomy's most difficult and ambitious challenges. Most exoplanets within our galaxy have been discovered using methods like the transit method, which detects tiny dips in a star's brightness when a planet crosses in front of it, and the radial velocity method, which measures a star's small wobbles caused by an orbiting planet's gravity. These techniques are effective for relatively nearby stars, but when applied to the vast distance of Andromeda, over 2 million light-years away, they become nearly impossible with current technology. To overcome this, astronomers are exploring new techniques. One of the most promising is gravitational microlensing, which relies on gravity's ability to bend and magnify light. When a massive object, such as a star or even a planet, passes in front of a more distant star, its gravity briefly focuses the light from the background star, making it appear brighter. If a planet orbits the foreground object, its presence can create a secondary, smaller, brightening a subtle signature that reveals its existence. Unlike traditional methods, microlensing doesn't require scientists to directly see the planet or even separate individual stars in distant galaxies. In 2020, astronomers reported what may be the first detection of a planet outside the Milky Way in the Whirlpool galaxy based on distortions in X-ray light from a distant binary system. Though still unconfirmed, this discovery proved that microlensing could one day help identify planets in other galaxies, including Andromeda. Andromeda's dense core, filled with overlapping stars, is an ideal environment for such microlensing events. By observing it consistently over long periods, astronomers could detect brief brightening patterns, potential evidence of distant planetary systems at work. However, even if planets are detected in Andromeda, confirming their details will be incredibly challenging. Within the Milky Way, follow-up studies can measure a planet's size, atmosphere, and even surface conditions. But for another galaxy, astronomers can only gather indirect evidence detecting the planet's presence, but not its composition or potential habitability. Determining whether such a world is rocky or gaseous, or whether it might contain water or air, remains far beyond today's capabilities. Future generations of powerful space telescopes may change that. As technology advances, instruments with higher sensitivity and resolution could allow scientists to study planets in distant galaxies in greater detail. In our own galaxy, astronomers use the concept of the habitable zone, the region around a star where conditions might allow liquid water to exist. Many of the exoplanets we've found so far orbit within such zones, raising the possibility that some could support life. But applying this concept to Andromeda is far more complex. Even if a planet were found at the right distance from its star, confirming whether it truly has water, an atmosphere, or any conditions suitable for life would require far more advanced tools than we currently possess. Still, given how similar Andromeda is to the Milky Way in structure and composition, it's very possible that planetary systems in that galaxy mirror the diversity found in our own, from barren, rocky worlds to massive gas giants and perhaps even planets with environments capable of sustaining life. There would be enormous gas giants orbiting their stars from great distances, rocky worlds locked tightly around their suns, and frozen planets drifting along the galaxy's outer edges. Some might resemble Earth in certain ways, while others could be unlike anything humanity has ever imagined. One of the most fascinating ideas is that planets might exist in regions of Andromeda that have undergone intense stellar interactions. Unlike our Milky Way, which has enjoyed a fairly calm history, Andromeda has collided and merged with many smaller galaxies over time. These cosmic mergers can disrupt existing planetary systems, throwing planets into unstable orbits or even ejecting them into the vastness of interstellar space. Many scientists believe this violent past could mean that Andromeda hosts countless rogue planets' worlds, wandering alone without a parent star. Such free-floating planets may be plentiful in the galaxy's extended halo, relics left adrift by ancient gravitational disturbances. If planets indeed exist in Andromeda, their environments would be deeply shaped by the unique conditions surrounding them. In the galaxy's central bulge, planets orbiting near the core would be exposed to extreme radiation, making the possibility of life there very low. In contrast, the spiral arms may offer more stable conditions, somewhat resembling those of the Milky Way. Yet the presence of supernova remnants, dense star clusters, and even medium-sized black holes across certain regions of Andromeda could significantly alter or interrupt planetary formation. The rapidly growing field of artificial intelligence is also being used in the search for distant worlds. Machine learning systems are now capable of detecting extremely faint patterns hidden in astronomical data, helping scientists identify potential planetary signals that traditional methods might overlook. With such advancements, we may soon witness the first confirmed discovery of planets within Andromeda itself, a milestone that could open a completely new era in the exploration of worlds beyond our own galaxy. Part 7. The feasibility of intergalactic travel. Traveling between galaxies is one of the most challenging and speculative frontiers in physics. The distances involved are so immense that even our fastest spacecraft appear painfully slow by comparison. Still, the dream of journeying beyond the Milky Way to faraway galaxies like Andromeda continues to captivate the human imagination. Over the years, scientists and engineers have proposed a range of theoretical ideas and advanced propulsion systems that might someday make these incredible voyages possible. The most obvious challenge is speed. Andromeda lies about 2.5 million light-years away. Even if a spacecraft could somehow travel at the speed of light, which is far beyond our current capability, it would still take 2.5 million years to arrive. For context, NASA's Parker Solar Probe, the fastest human-made object, travels at around 430,000 miles per hour. At that rate, a mission to Andromeda would last more than 4,000 times longer than the entire span of human civilization. Clearly, intergalactic travel would require a completely new form of propulsion technology. Einstein's theory of relativity predicts that as an object nears light speed, time slows down for those on board. This means that although the trip might take millions of years from Earth's perspective, passengers could experience only decades or even years passing. Yet reaching such speeds remains far beyond what current technology allows. Chemical rockets, the kind that power all present-day spacecraft, are hopelessly inadequate. Researchers are now turning to more advanced ideas such as nuclear fusion, antimatter drives, and even harnessing the fundamental energy of space itself. One promising concept is the light sail, powered by powerful laser beams. The Breakthrough Starshot initiative is currently developing small probes that could reach the nearby Alpha Centauri system by accelerating to about 20 of light speed using concentrated laser energy. To scale such technology for intergalactic missions would require unimaginable amounts of power, but in principle, a massive laser array could push a spacecraft close to light speed. Another theoretical solution is antimatter propulsion. Antimatter holds the highest known energy density, releasing vast amounts of power when it interacts with normal matter. A craft using carefully controlled antimatter reactions could achieve incredible velocities far beyond what chemical or even nuclear rockets could reach. However, creating and storing antimatter safely in large quantities remains one of the biggest unsolved challenges in modern physics. If a spacecraft could indeed approach light speed, relativistic effects would compress time for those aboard, allowing travelers to reach Andromeda within a few decades of subjective time. Some theorists have also suggested using black holes or other cosmic phenomena to aid travel. One famous idea, the Alcubierre warp drive, proposes bending space-time itself, contracting space in front of a ship, and expanding it behind, effectively enabling faster-than-light motion without violating Einstein's laws. Though entirely theoretical, this concept requires exotic forms of energy, such as negative mass, which have never been observed. Another possibility lies in natural shortcuts across the cosmos. If wormholes truly exist, they could form tunnels linking distant points in space-time, making travel between galaxies nearly instantaneous. However, no solid evidence for wormholes has ever been found, and even if they do exist, keeping one open long enough for safe passage would demand unknown and likely unstable forms of exotic matter. Still, many physicists speculate that advanced civilizations, if any exist, might have already unlocked such mechanisms. Beyond the issue of propulsion, the question of survival is equally critical. An intergalactic voyage lasting thousands or even millions of years would require new ways to preserve or sustain life. One possible solution is suspended animation, placing travelers in a state of deep hibernation for centuries. Scientists are actively studying hibernation processes found in certain animals to see if they could be adapted for space travel. Cryogenic freezing is another proposed method, though safely reviving frozen humans remains an unsolved biological problem. A more practical alternative could be sending self-replicating robotic probes instead of humans. Originally proposed by mathematician John von Neumann, this concept envisions spacecraft equipped with artificial intelligence and advanced manufacturing systems. These probes could use local materials to construct replicas of themselves and continue exploring indefinitely, spreading information throughout the cosmos without requiring human crews. Over long timescales, such autonomous explorers could reach distant galaxies like Andromeda, gather data, and transmit it back across the void. Although ideas like these remain purely theoretical for now, the rapid pace of technological progress suggests that concepts once confined to science fiction might one day become achievable. Crossing the immense expanses between galaxies introduces a range of problems that go far beyond simply moving fast. The vastness of intergalactic space tests every limit: endurance, precision, and survival. Any spacecraft attempting to leave the Milky Way and travel toward Andromeda would need to endure harsh conditions, maintain power across unthinkable distances, and function without the possibility of resupply or repair for millions of years. One of the first concerns is protection from deep space hazards. Inside our solar system, astronauts benefit from Earth's magnetic field and the Sun's heliosphere, both of which help block a portion of harmful cosmic radiation. But once a ship moves beyond this protective zone, it is exposed to a relentless bombardment of high-energy particles, cosmic rays accelerated by supernova and black holes throughout the galaxy. Over extended periods of time, constant exposure to this radiation would pose severe dangers to any human crew, damaging DNA, raising cancer risks, and slowly wearing down onboard electronics. Protecting against such radiation would require either extremely thick layers of shielding, which would greatly increase the spacecraft's mass, or advanced active shielding systems capable of generating artificial magnetic fields. Even with proper radiation defenses, travelers venturing between galaxies would still have to confront the overwhelming emptiness of deep space. Unlike within a solar system, where planets, moons, and asteroids occasionally provide solid ground or resources, the space between galaxies is almost completely barren. There are no natural outposts or refueling stations. Every bit of fuel, water, food, and spare material would have to be carried from the very beginning of the mission. This presents an immense engineering challenge: how to store, preserve, and manage all necessary supplies for a journey that could last millions of years. Current chemical rockets are far too inefficient for such a task. More advanced propulsion systems, such as nuclear-powered engines or ion drives, offer much better efficiency but would still struggle to sustain a voyage lasting millennia. One imaginative concept proposes that a spacecraft could refuel itself while traveling. The Bussard ramjet, for instance, is a theoretical engine that uses large electromagnetic fields to collect hydrogen atoms from the interstellar medium and then fuse them to create thrust. Although it has never been built or proven, it illustrates the kind of unconventional thinking required for truly long-distance space exploration. Navigation introduces yet another serious obstacle. Inside our solar system, spacecraft determine their positions using signals from Earth, with planets and other bodies providing familiar landmarks. But once a ship leaves the galaxy, the universe becomes an almost featureless void. Stars grow dim, and recognizable reference points fade into the cosmic background. Any craft bound for Andromeda would need an entirely autonomous navigation system, capable of constantly correcting its course using faint celestial markers. One promising method under study is pulsar-based navigation, which uses the precisely timed radio signals emitted by rapidly spinning neutron stars to calculate position. Over a voyage spanning thousands of years, mechanical degradation would be inevitable. Micrometeoroids and sparse clouds of interstellar dust, though rare, could gradually erode the spacecraft S-hull as it moves at tremendous speeds. Even the smallest impacts could accumulate over centuries, weakening protective armor and threatening internal systems. Future spacecraft might need self-healing materials or autonomous maintenance robots capable of performing continuous repairs. If the ship relies on rotating sections to simulate gravity, those moving parts would need to operate flawlessly for millennia without breaking down. Communication across such distances adds another nearly impossible challenge. Today, radio signals sent from Earth to the farthest probes, like Voyager 1, take over 22 hours to arrive. For a ship journeying toward Andromeda, communication delays would stretch from years to centuries, and eventually to thousands of years. A message sent back after a millennium of travel would reach an Earth that might no longer resemble the world that launched the mission. This means any intergalactic vessel would have to be fully autonomous and self-reliant, capable of operating entirely without human guidance or resupply. Solar energy, which powers many spacecraft near Earth, would be almost useless in the dark void between galaxies where starlight is too weak to harvest. Instead, ships would require a long-lasting internal energy source, such as fusion reactors or other compact sustainable systems. The problem isn't only generating power, but maintaining it over vast timescales without needing refueling. If human passengers were on board, maintaining life support would be an even greater concern. A truly closed ecosystem where air, water, and nutrients are endlessly recycled would be essential. Even on the International Space Station, recycling is not perfect and depends on frequent resupply from Earth. A deep space ship, on the other hand, would need a nearly flawless system capable of supporting life for generations. Hydroponic or aeroponic farming might provide food, but ensuring biological balance and genetic stability over such long periods is a challenge scientists have yet to solve. The psychological burden of extreme isolation also poses unique risks. On a multi-generational voyage, crew members would live and die entirely aboard the ship, never returning to Earth and never seeing the destination in their lifetimes. Entire societies would have to evolve in isolation, developing their own traditions, governments, and cultures as centuries pass. Maintaining mental health, social harmony, and cultural continuity would be as crucial as the ship's physical systems. Some of these difficulties could be reduced by replacing humans with machines. Robotic explorers or artificial intelligences built to operate independently and repair themselves could carry out such missions without needing food, air, or emotional support. Still, machines too can fail, their components wear out, and even the most advanced software can degrade or become corrupted. Self-replicating probes, capable of creating copies of themselves from raw materials encountered along the way, may offer a solution, ensuring that the mission continues indefinitely even if individual units fail. Part 8. Simulating the future. When Andromeda meets the Milky Way, the fate of our galaxy is no longer a mystery. Thanks to powerful computer simulations, astronomers can now predict in detail what will happen when the Milky Way and Andromeda finally collide, a cataclysmic but graceful event expected to unfold several billion years from now. Using decades of observational data and advanced modeling, scientists have recreated this slow-motion cosmic dance, revealing a future both chaotic and awe-inspiring. Andromeda is currently approaching the Milky Way at a velocity of about 110 kilometers per second. At this pace, the first close encounter is projected to occur roughly 4.5 billion years from today. Despite the dramatic description of a collision, it will not resemble the violent crashes we associate with asteroids. The enormous distances between individual stars mean that direct impacts will be exceedingly rare. Instead, the immense gravitational pull between the galaxies will distort their shapes, drawing out long, elegant tidal streams of stars and gas. These tidal forces will stretch and twist both galaxies into spiraling arcs before they finally merge into a single, much larger structure. Astronomers feed precise data on each galaxy's mass, motion, and composition into powerful computers, allowing them to model how gravity will sculpt their interaction. By running countless variations of these simulations, researchers can predict multiple outcomes, though all point toward the same general result: a prolonged complex merger that will see each galaxy pass through the other several times before settling into a new form. The first encounter will be the most spectacular. As they draw close, the mutual gravitational tug will warp their spiral arms, flinging great streams of stars into the darkness of intergalactic space. Andromeda's dense core will likely plunge straight through the Milky Way's heart, dragging enormous quantities of gas along with it. This will trigger waves of new star formation as clouds of gas compress under pressure, lighting up the galaxies with countless young, brilliant stars. Some will cluster into massive star-forming regions, while others will eventually collapse into black holes, adding to the growing number of these enigmatic objects within the merged system. As the interaction continues, repeated close passes will further tear apart both galaxies. Their once orderly spiral arms will be stretched and shredded into long tidal tails. Some stars will be ejected completely, hurled into the intergalactic void where they will wander alone for billions of years. Others will gradually settle into new orbits as the galaxies blend their stellar populations into one. After billions of years of these gravitational dances, the two systems will finally stabilize into a single unified galaxy. Simulations suggest that this end product will not be a spiral like the Milky Way or Andromeda, but a vast elliptical galaxy. This transformation occurs because the violent interactions disrupt the structured orbits of stars, replacing the graceful rotation of spiral arms with random, three-dimensional motion. The result is a smooth, rounded shape, a golden, glowing remnant of two once spiral giants. In this new elliptical form, stars will mix more thoroughly, erasing the distinct spiral patterns that defined each parent galaxy. Without the organized rotation that maintains spiral arms, the merged galaxy will become more uniform and featureless over time. Its color will shift gradually from the bright blues of active star-forming regions to a warmer golden tone, the mark of older, cooler stars dominating the light. Scientists have even given this future galaxy a name, Milkomeda, a blend of Milky Way and Andromeda. It will be larger than either of its predecessors, and at its center will likely reside a supermassive black hole formed by the merger of the central black holes from both galaxies. By the time this titanic event occurs, our Sun will be nearing the end of its life. About 5 billion years from now, it will swell into a red giant, rendering Earth uninhabitable. Yet if humanity or any intelligent life derived from it survives and expands into the stars, the galactic merger could bring new opportunities. The infusion of fresh gas from Andromeda will spark waves of star formation, creating new worlds that may someday support life. Although star-to-star collisions will be rare, gravitational effects will reshape planetary systems. Some may be thrown into new orbits, others could be ejected entirely into intergalactic space. There's even a small chance our solar system could be displaced, drawn deeper into the new galaxy, or flung outward into the vast dark beyond. Eventually, Milky will settle into a quieter phase as the chaos subsides. Yet, the story may not end there. Some models predict that the newly merged galaxy will, in time, collide with other nearby systems, continuing the cosmic cycle of destruction and creation. As the universe expands, distant galaxies will drift ever farther away, their light stretching into invisibility, leaving Milky and its remaining companions to drift together in a silent, ever-darkening cosmos. In the distant epochs to come, only the nearest galaxies, those that have already collided or remain gravitationally tethered, will continue to be visible to any observer. Long after the Great Merger, Milky will endure as a solitary beacon, an island galaxy surrounded by the vast emptiness of an ever-fading universe. It will stand among the final grand structures left in a darkening cosmos, its stars shining against an increasingly desolate backdrop. Across the universe, countless examples illustrate this process of galactic encounters, ranging from early-stage collisions to the final blended remnants of elliptical galaxies born from them. By examining other galaxies currently locked in such interactions, astronomers gain living laboratories with which to compare their theoretical simulations. These observations refine computational models, allowing a deeper understanding of the gravitational and dynamical forces at work during cosmic mergers. Though humanity will never observe our own galactic collision unfold directly, the ability to model and predict these vast transformations offers a window into a future sky that will look utterly unlike the one we know today. Both Andromeda and the Milky Way are dominant members of the Local Group, a gravitationally bound cluster containing over 50 galaxies. Each possesses hundreds of billions of stars, broad spiral arms, and a central supermassive black hole anchoring its core. Yet subtle differences in their scale, structure, and stellar makeup reveal the divergent evolutionary paths that shaped them. Andromeda's visible disk is considerably wider, measuring nearly 220,000 light-years across, while the Milky Way spans between 100,000 and 160,000 light-years. However, estimates suggest that our galaxy may actually hold a slightly greater total mass due to its dense nucleus and expansive halo of dark matter. These variations raise important questions about how galaxies accumulate material and grow over cosmic time. Andromeda's broad disk hints that it has consumed numerous smaller galaxies, absorbing their stars and gas to build its extensive structure. Containing an estimated trillion stars, more than double the Milky Way's 200–400 billion, Andromeda likely experienced either a more efficient era of star formation or a longer history of mergers. Yet, despite its greater stellar count, its current rate of forming new stars is markedly slower. In contrast, the Milky Way still shows vigorous star-forming regions, marked by brilliant blue clusters and glowing nebulae within its spiral arms. These active regions reveal that our galaxy remains in a dynamic phase of stellar birth, whereas Andromeda appears to be transitioning into a quieter, more mature stage of evolution. Andromeda's central bulge is notably larger and more luminous, populated with ancient red stars densely packed around its nucleus. This structure suggests a history filled with major collisions that once channeled immense amounts of gas into the core, triggering intense bursts of star formation. The Milky Way's central bulge, though also rich in old stars, is less prominent, implying a gentler evolutionary path or distinct patterns of internal star migration. The black hole at Andromeda's center, designated M31, is believed to possess a mass roughly 140 million times that of the Sun. By comparison, Sagittarius A, the Milky Way's central black hole, weighs in at about 4 million solar masses. This stark difference implies that Andromeda's nucleus has endured more dramatic cosmic events, perhaps absorbing multiple smaller black holes through successive mergers. Such a massive core exerts a powerful gravitational influence on surrounding stars, creating a more energetic and turbulent inner environment. Both galaxies exhibit graceful rotation, their spiral arms sweeping through space in vast celestial motion. Yet Andromeda spins more rapidly, with stars orbiting at approximately 250 kilometers per second, compared to the Milky Way's 220 kilometers per second. This increased velocity may result from its denser stellar population and larger bulge, which alter the balance of gravitational forces within its disk. Despite these distinctions, both share the same essential framework, a barred spiral form. Their elongated central bars act as stellar highways, channeling material toward their cores, fueling ongoing star formation, and feeding their central black holes. Such structures are common in mature spirals and are thought to arise naturally through gravitational instabilities over time. Surrounding both galaxies are extensive systems of smaller satellites, dwarf galaxies, and globular clusters that accompany them through space. The Milky Way's companions include the Large and Small Magellanic Clouds, as well as the Sagittarius dwarf galaxy, currently being torn apart by tidal forces. Andromeda's companions, such as M32 and M110, display signs of past gravitational encounters that shaped their present forms. Interestingly, recent data show that Andromeda's satellites lie in a surprisingly thin, ordered plane, while those orbiting the Milky Way are more randomly scattered. This contrast hints at fundamental differences in their past interactions and formation histories. A large portion of Andromeda's complexity is veiled behind thick curtains of interstellar dust that block visible light, concealing much of the galaxy's true form. This dust acts as a cosmic shroud, making it difficult to observe the intricate details hidden within. Infrared light, however, penetrates these obscuring layers, allowing astronomers to unveil the galaxy's hidden structure. Through infrared observation, researchers have gained an entirely new perspective on Andromeda, one that reveals both its composition and the processes shaping its evolution. Among the most significant discoveries from infrared imaging is the detailed view of Andromeda's dust lanes. In visible wavelengths, these appear as dark streaks weaving through its spiral arms, masking the stars behind them. But in infrared light, those same regions glow with warmth, outlining a complex network of filaments that trace the framework of the galaxy itself. These dusty pathways are essential for star formation, as they contain the cold molecular gas that eventually collapses to form new stars. By studying these areas, scientists can identify the locations where stellar nurseries are preparing to ignite long before they are seen in optical light. At the galaxy's heart, the density of stars is so great that their collective brightness overwhelms visible light instruments, rendering the core nearly featureless. Infrared telescopes cut through that glare, exposing the detailed architecture surrounding Andromeda's supermassive black hole. They reveal a dense, rotating disk of stars orbiting under the influence of intense gravitational forces. This region, which appears as a brilliant blur in ordinary light, becomes a dynamic and intricate environment in the infrared, where the individual motions of stars can be resolved and studied. Older stars, especially red giants, emit the majority of their radiation in the infrared spectrum, making them key traces of galactic history. Mapping their distribution allows astronomers to reconstruct the evolutionary story of Andromeda, tracing how interactions and mergers redistributed stars over billions of years. Collisions between galaxies often leave behind faint trails of stars and dust known as tidal streams. These elongated remnants can be difficult to detect in visible light, but become apparent in infrared surveys, where the residual warmth of interstellar dust reveals their shapes. Infrared technology also provides access to a population of dim, low-mass objects that remain invisible at optical wavelengths. Among these are brown dwarfs, objects too small to sustain nuclear fusion, yet too large to be considered planets. They radiate primarily in infrared, making them detectable only through such instruments. Observations have uncovered numerous brown dwarfs scattered throughout Andromeda, filling in critical gaps in our understanding of the galaxy's stellar makeup. By cataloguing these elusive objects, scientists gain insight into the lower boundary of star formation and the conditions that govern it. Part 9. Radio Whispers: Unconventional Views of Andromeda. While optical and infrared observations capture the visible and thermal components of Andromeda, radio astronomy reveals a completely different perspective, one shaped by magnetism, cold gas, and ancient cosmic signals. Radio waves allow scientists to peer into regions otherwise invisible, detecting phenomena that unfold over immense timescales. A cornerstone of radio studies involves mapping neutral hydrogen, the most abundant element in the universe. Neutral hydrogen emits a distinctive signal at a wavelength of 21 centimeters, known as the hydrogen line. This faint emission provides astronomers with a powerful tool to chart the distribution and movement of gas throughout Andromeda's disk. By observing at this wavelength, scientists can build comprehensive maps that reveal the galaxy's gaseous skeleton, identifying regions where new stars are forming and how its spiral arms continue to evolve. Radio surveys have revealed that Andromeda's gaseous disk extends far beyond its visible edges. While its luminous core spans roughly 220,000 light-years, its hydrogen envelope stretches much farther into the surrounding intergalactic medium, gradually blending with the diffuse cosmic background. These radio observations expose the hidden breadth of Andromeda, showing that the galaxy's influence, both gravitational and material, reaches far beyond what the eye can see. Unlike visible light, which primarily reveals the physical structure of stars and dust, radio signals can uncover the invisible forces shaping galaxies, especially magnetic fields. When charged particles spiral along these magnetic field lines, they emit synchrotron radiation, a faint yet consistent signal detectable by radio telescopes. Mapping this emission has revealed that Andromeda possesses a large-scale, organized magnetic field stretching across much of the galaxy. This field influences the movement of cosmic rays, guides the flow of interstellar gas, and shapes regions where new stars are born. Radio astronomy has also revealed pulsars within Andromeda, rapidly spinning neutron stars that emit beams of radiation in precise intervals. Despite Andromeda being over 2 million light-years away, sensitive radio telescopes on Earth can detect these rhythmic pulses, offering rare insights into how massive stars end their lives beyond our own galaxy. At Andromeda's center lies M31, a supermassive black hole that, while less active than those in quasars or radio galaxies, still emits a faint radio glow. This emission comes from charged particles whirling around its intense magnetic fields. By studying these radio signals, astronomers can probe the black hole's accretion environment, learning how it consumes nearby matter and affects its surroundings. Beyond the central black hole, Andromeda contains several mysterious radio sources that lack visible or infrared counterparts. Some of these may be ancient supernova remnants, where expanding shock waves energize gas and dust, producing strong radio emissions. Others could mark active star-forming regions, where massive young stars ionize the surrounding gas. Pinpointing and classifying these sources remains an ongoing challenge, demanding increasingly sensitive instruments and sophisticated data analysis. Radio astronomy has also become a cornerstone in the search for extraterrestrial intelligence, CT. Although no artificial signals have been found, astronomers have aimed radio telescopes at Andromeda, searching for structured or repeating patterns, signs that might indicate an intelligent origin. The upcoming Square Kilometre Array, SKA telescope, will dramatically enhance this search, mapping Andromeda's magnetic field in greater detail, detecting faint hydrogen emissions, and uncovering hidden radio sources that remain beyond current reach. Through radio astronomy, Andromeda whispers across the cosmic dark, revealing its secrets to those patient enough to listen. One of the most remarkable effects of gravity is its ability to bend light, a phenomenon known as gravitational lensing. Massive objects like galaxies can act as natural telescopes, magnifying and distorting the light from far more distant galaxies behind them. In this sense, Andromeda itself can serve as a cosmic lens, helping astronomers study the earliest galaxies formed billions of years ago. Without Andromeda's gravitational magnification, many of these faint background galaxies would remain invisible, even to the most powerful telescopes. Detecting these lensing effects, however, is particularly challenging in Andromeda. Its own stars, dust, and gas create significant foreground noise, which can obscure the much fainter lensed images of background galaxies. To overcome this, astronomers use advanced image processing techniques to subtract the bright local features, allowing them to isolate subtle distortions in the light. These patterns, stretched arcs or duplicated images, serve as clear signatures of gravitational lensing. Lensing doesn't just help us study distant galaxies. It can also reveal objects within Andromeda itself. When a single star or compact object briefly magnifies the light of a background star, the event is called microlensing. These short-lived flashes allow astronomers to detect otherwise invisible bodies, rogue planets, black holes, or dense clumps of dark matter. Microlensing has already revealed planets in our own galaxy, and applying the same methods to Andromeda may one day confirm the first extragalactic planets. Gravitational lensing also serves as a cosmic laboratory for physics. Light that travels around a massive object doesn't just bend it, experiences time delays. When multiple lensed images of a flickering quasar appear, their light arrives at slightly different times. Measuring these delays can refine estimates of the Hubble constant, helping scientists better understand how quickly the universe is expanding. The concept of wormholes emerges directly from Einstein's theory of general relativity. These hypothetical tunnels in space-time could connect two distant points, perhaps even two galaxies, through a hidden passage known as an Einstein-Rosen bridge. In theory, a stable wormhole between the Milky Way and Andromeda could enable near-instantaneous travel, eliminating the need for propulsion altogether. Yet, according to relativity, a natural wormhole would collapse almost instantly after forming. To keep one open, scientists propose the existence of exotic matter with negative energy density, a form of matter not yet observed. This exotic material would counteract gravity's inward pull, stabilizing the tunnel S structure long enough for travel. Detecting wormholes, if they exist, would require indirect evidence. Researchers suggest searching for unusual gravitational lensing patterns distinct from those produced by black holes. Some even speculate that certain black holes might actually conceal wormhole entrances, though observations including those of Sagittarius A Chas, the Milky Way's central black hole, have not yet supported this theory. Even if a stable wormhole existed, navigating it would pose immense challenges. A spacecraft approaching the entrance could encounter extreme tidal forces or lethal radiation fields. The tunnel itself might not be smooth or linear. Space-time inside could twist or compress unpredictably. Additionally, the effects of time dilation could become profound, meaning a traveler might arrive not only at another location, but potentially at another point in time. Such possibilities raise profound questions about causality and paradoxes, where journeys through wormholes might allow one to arrive before departing. Though purely theoretical for now, wormholes continue to intrigue scientists as potential gateways to both intergalactic travel and time manipulation ideas that stretch the limits of modern physics and imagination alike. Other theoretical constructs may also provide shortcuts across the universe, functioning as natural or artificial bridges through space-time. One such concept involves cosmic strings infinitesimally thin, high-energy filaments that may have formed during the universe's earliest moments. Some theories propose that if two cosmic strings were to move past one another at near-light speeds, the immense distortion they create could warp space-time in such a way as to allow for shortcuts between distant points in the cosmos. Though purely hypothetical, these structures could represent an alternative mechanism to traditional wormholes, natural conduits, through the very fabric of space itself. Another intriguing idea lies in the quantum foam that makes up space-time at the smallest scales. At this quantum level, space-time may constantly fluctuate, forming and collapsing tiny microscopic wormholes that appear and vanish within fractions of a second. If this model proves correct, then an advanced civilization might one day discover how to stabilize and enlarge these quantum wormholes, transforming them into traversable passages across vast cosmic distances. This concept is far beyond the reach of current physics or technology, but it illustrates the immense untapped potential hidden within space-time's underlying structure. If a civilization possessed the ability to harness tremendous amounts of energy, perhaps on the scale of entire stars, it could, in theory, manipulate space-time directly. Certain models suggest that generating and controlling negative energy density might allow for the artificial construction and stabilization of a wormhole. Such mastery would redefine the limits of exploration, enabling movement not just across galaxies, but potentially between universes. These ideas raise a profound question. Could the cosmos be interconnected by a hidden network of space-time tunnels? Some theories suggest that our universe might be part of an immense cosmic web, a system of interlinked wormholes connecting galaxies, clusters, and perhaps even parallel universes. Though still theoretical, the study of these possibilities continues to advance our understanding of gravity, quantum mechanics, and the fundamental geometry of reality itself. Even if wormholes are never found or constructed, their exploration has already deepened humanity's grasp of space-time and the forces that shape the universe. Part 10. Extragalactic habitability in Andromeda. The fundamental ingredients for life as we understand it remain constant across the cosmos. A stable orbit, a temperate environment where liquid water can exist, and an atmosphere capable of supporting complex chemistry. While these parameters are well established for exoplanets within the Milky Way, extending them to Andromeda introduces new challenges and layers of uncertainty. Because of its vast distance, individual exoplanets in Andromeda cannot yet be observed directly. Instead, astronomers rely on indirect evidence, such as the Galaxy S stellar composition, metallicity, and regions of active star formation, to estimate where life might have the best chance to emerge. One of the key factors in planetary habitability is the distribution of metal-rich stars, those containing heavier elements like carbon, oxygen, and nitrogen. These elements are the building blocks of atmospheres, oceans, and biological molecules, all produced in earlier generations of stars and dispersed through supernova explosions. Andromeda S, mixed population of young and ancient stars, suggests that planet formation is ongoing. Younger metal-rich stars, particularly those within the spiral arms, are prime candidates for hosting rocky planets within their habitable zones. However, Andromeda S' violent merger history has also shaped its structure and environment. Collisions with smaller galaxies can destabilize planetary orbits, trigger intense radiation events, or eject planets into interstellar space. Thus, regions near the galactic core or in areas of high stellar density may be too chaotic for long-term stability, while the outer spiral arms could provide more tranquil conditions suitable for life's development. In the Milky Way, scientists have already discovered numerous water-bearing exoplanets and icy moons that may conceal subsurface oceans warmed by internal heat. This suggests that life might not be limited to planets in traditional habitable zones. It could thrive beneath ice-covered worlds orbiting gas giants. Detecting such environments in Andromeda, however, poses extraordinary challenges. Even with our most advanced telescopes, resolving details of individual planets or moons at that distance remains beyond current capability. Some researchers speculate that non-carbon-based life, such as silicon-based organisms, might exist in extreme environments that would be lethal to Earth-like life. Given Andromeda S' diversity of star types from long-lived red dwarfs to massive blue giants, the potential range of planetary environments is vast. Worlds with dense ammonia or methane atmospheres might host entirely different biochemical systems, expanding the definition of habitability beyond terrestrial expectations. Within our own galaxy, astronomers search for biosignatures, specific combinations of gases like oxygen, methane, and carbon dioxide that indicate active biological processes. Detecting such signals in Andromeda would be exponentially more difficult, but future telescopes could analyze the atmospheric spectra of its exoplanets for hints of imbalance, a possible indicator of life. For instance, a coexistence of oxygen and methane could suggest biological activity, even if the exact nature of that life remains unknown. If intelligent life had ever arisen in Andromeda, it might have left technological signatures. These could include artificial radio emissions, pulsed laser signals, or vast megastructures such as Dyson spheres, hypothetical constructs built to capture the energy output of entire stars. Such objects, if they existed, would radiate distinct infrared signatures, detectable with sensitive instruments. However, identifying such evidence is an enormous challenge. Alien civilizations may communicate using methods entirely beyond human comprehension, or they may have vanished long ago. Andromeda S' immense age adds another layer of intrigue. Star formation there has been active for billions of years, meaning that intelligent life could have appeared long before humanity's existence, or it could already have come and gone. If humanity were ever to undertake the extraordinary task of colonizing the Andromeda Galaxy, the mission would demand a level of coordination, endurance, and innovation unprecedented in history. Such an endeavour would require not only revolutionary propulsion technologies and interstellar engineering, but also the creation of self-sustaining ecosystems capable of surviving for millennia in transit. This hypothetical framework, sometimes referred to as the Andromeda Protocol, would serve as a long-term blueprint for expanding civilization beyond the Milky Way. It would encompass the design of generation ships, the use of artificial intelligence to maintain systems during multi-thousand-year voyages, and the implementation of genetic preservation programs to ensure humanity's survival across cosmic timescales. Though the idea of reaching Andromeda remains distant, the very act of planning for it pushes the boundaries of science, imagination, and human potential. It stands as a testament to our species' enduring curiosity and our relentless drive to explore, adapt, and endure among the stars. The Andromeda Protocol, a theoretical blueprint for humanity's expansion beyond the Milky Way, would serve as a guiding framework for a venture unlike any ever attempted. It would outline the stages of development required for such a mission, from the first robotic explorations to the establishment of self-sustaining colonies in another galaxy. This concept represents the natural evolution of human ambition, the next logical step after interplanetary and interstellar exploration. The first phase of the protocol would depend on the development of intergalactic propulsion systems capable of traversing the immense distances between galaxies. Reaching Andromeda, located more than 2 million light-years away, would require breakthroughs far beyond current propulsion technologies. Concepts such as antimatter engines, fusion-based drives, or even the speculative Alcubierre warp drive have been proposed as potential means to achieve practical intergalactic travel. These technologies, if ever realized, would fundamentally change humanity's relationship with space and time. Before any human presence could be established in Andromeda, robotic probes would take the lead. These autonomous explorers would be equipped with advanced artificial intelligence, capable of independent decision-making and long-duration operation. Unlike present-day probes, which depend on delayed radio communications with Earth, intergalactic probes would need complete autonomy. They would survey Andromeda's star systems, identify potentially habitable worlds, and map the distribution of valuable resources. Communication with Earth could rely on speculative methods such as quantum entanglement or other forms of instantaneous data transfer still beyond our understanding. Once a suitable planetary system had been identified, the next phase would focus on infrastructure. Self-replicating robotic factories machines designed to construct duplicates of themselves could be dispatched to extract raw materials from asteroids or planetary surfaces. Using advanced nanotechnology and 3D printing, these systems would build essential components such as orbital habitats, research stations, and energy collection networks. Over time, entire industrial ecosystems could arise, capable of sustaining human life long before the first settlers arrive. Terraforming might begin even before human colonization. Selected planets could undergo atmospheric modification using bioengineered microorganisms capable of producing oxygen or altering chemical compositions. The slow transformation of alien environments could create habitable conditions over centuries, preparing the way for future generations. These efforts would mark the beginning of humanity as an attempt to shape an entirely new world from lifeless rock and gas. The transport of human settlers to Andromeda would represent one of the most complex challenges of the entire protocol. Unless faster-than-light travel becomes possible, the journey would take millennia, requiring the construction of vast generational starships, sometimes called world ships. These colossal vessels would function as self-contained civilizations, carrying entire ecosystems, manufacturing facilities, and living quarters for populations that might live and die among the stars without ever touching a planetary surface. Within such ships, knowledge would be preserved through education and culture, ensuring continuity across generations. The crew's descendants would inherit the mission, maintaining a purpose that transcends individual lifetimes. If human hibernation technology becomes feasible, passengers could instead travel in deep stasis, awakening only upon arrival. Alternatively, mind uploading could allow human consciousness to be digitized and transmitted, stored within artificial systems, and later embodied through robotic or bioengineered forms once the destination is reached. Upon arrival in Andromeda, the establishment of a foothold would require careful coordination. The first human presence might exist as large orbital habitats constructed near resource-rich planetary systems. These habitats would serve as logistical centers overseeing exploration, mining, and surface landings. Over time, they would expand into networks of interconnected colonies spanning multiple systems. Terraforming and resource extraction would continue in parallel, gradually transforming Andromeda from a distant frontier into a new domain of human civilization. A critical component of the Andromeda Protocol would be the creation of self-sustaining ecosystems. Unlike Earth, whose biosphere evolved naturally over billions of years, artificial colonies would require closed-loop systems capable of recycling air, water, and nutrients indefinitely. Genetic engineering could play a vital role, producing crops and microorganisms adapted to alien conditions. Artificial biospheres, powered by renewable energy, would ensure long-term survivability independent of resupply from Earth. Communication with the Milky Way would pose profound limitations. Even with advanced methods, information exchanges could take millions of years, effectively isolating Andromeda-esque colonies. Over such timescales, distinct societies could evolve, shaped by their environments and technologies. These civilizations might develop new languages, cultures, and even biological adaptations, gradually diverging from their Earth-born origins. If intelligent civilizations already exist within Andromeda, contact would present unprecedented challenges. The Andromeda Protocol would require strict ethical and procedural frameworks for first contact scenarios, ensuring that encounters are approached with caution and mutual respect. Humanity would need to navigate issues of coexistence, territorial rights, and communication with species potentially billions of years more advanced or fundamentally different in form and perception. Defense would also be an essential consideration. Settlements would need to prepare for natural cosmic threats such as asteroids, gamma-ray bursts, and rogue black holes. Advanced monitoring systems, autonomous defense drones, and protective magnetic fields could mitigate such dangers. However, the possibility of hostile encounters, whether from native life or rival species, would necessitate the development of both defensive and diplomatic strategies. Despite these challenges, the colonization of Andromeda would represent the greatest milestone in the history of humankind. It would mark the transition from a species confined to one galaxy to an intergalactic civilization. Such an endeavor would redefine the boundaries of survival and intelligence, transforming humanity into an agent of cosmic continuity. The Andromeda Protocol would not merely be a technological project, it would be a statement of existence, a bridge between imagination and reality, and a testament to the enduring drive of life to expand beyond every horizon. While the Andromeda Protocol represents a future vision, present-day astronomy is already laying the foundation for understanding our neighboring galaxy. One of the most significant advancements has come from the development of large optical telescopes, capable of capturing light from distant galaxies in unprecedented detail. Instruments such as the Extremely Large Telescope, ELT, in Chile, with a primary mirror over 30 meters wide, promise to reveal faint celestial structures never before seen. Adaptive optics, which compensate for distortions caused by Earth's atmosphere, have revolutionized ground-based observation. By continuously adjusting mirror surfaces to counteract atmospheric turbulence, telescopes can now achieve image resolutions comparable to those obtained from space. Space-based observatories, however, remain the pinnacle of clarity. The Hubble Space Telescope provided humanity with its first detailed glimpses of Andromeda, revealing its spiral arms, star clusters, and galactic core in exquisite detail. Building upon Hubble's legacy, the James Webb Space Telescope, JWST, has extended humanity's vision into the infrared spectrum, allowing astronomers to peer through clouds of interstellar dust to study the birthplaces of stars and the structure of distant planetary systems. In the case of Andromeda, JWST's data has shed new light on its stellar evolution, gas dynamics, and the hidden processes shaping its spiral form. Beyond optical instruments, radio astronomy continues to play a vital role in extragalactic research. The upcoming Square Kilometre Array, SKA, a massive network of radio dishes spanning continents, will be among the most powerful tools ever constructed for studying galaxies like Andromeda. By tracking radio emissions, scientists can trace the movement of hydrogen gas, observe galactic magnetic fields, and monitor long-term stellar activity. Unlike optical telescopes, radio observatories can operate under virtually any weather condition, providing constant observation capabilities. Spectroscopic analysis has become another cornerstone of galactic science. By dispersing light into its constituent wavelengths, astronomers can determine a star's chemical composition, temperature, and motion. Facilities such as the Keck Observatory employ advanced spectrographs to study Andromeda's central regions, measuring stellar velocities and confirming the existence of its supermassive black hole. Spectroscopy also reveals the age distribution of stars, allowing researchers to reconstruct Andromeda's evolutionary history and its past galactic mergers. Meanwhile, missions like the European Space Agency's Gaia Observatory have transformed our understanding of stellar motion within the Milky Way. Applying similar methods to Andromeda enables astronomers to model its dynamic structure, tracing star streams left behind by absorbed dwarf galaxies and predicting future interactions, including its eventual merger with the Milky Way billions of years from now. Modern observatories, such as the Vera C. Rubin Observatory, generate immense datasets containing images of millions of galaxies. Analyzing this data requires sophisticated algorithms capable of identifying patterns invisible to the human eye. Artificial intelligence now plays a pivotal role, classifying galaxies, detecting anomalies, and predicting gravitational interactions that might lead to future collisions. In the case of Andromeda, AI-assisted analysis has uncovered subtle tidal features and stellar streams, offering new clues about its complex history. The emergence of gravitational wave astronomy has added an entirely new dimension to this field. Instruments like LIGO and Virgo have already detected the faint ripples in our space-time caused by merging black holes and neutron stars. Future missions such as the Laser Interferometer, Space Antenna, LISA, could detect gravitational waves from supermassive black hole mergers within galaxies like Andromeda. Such signals would provide insight into the invisible dynamics shaping the hearts of galaxies. Another growing frontier is neutrino astronomy, the study of nearly massless particles capable of passing through entire planets without interaction. Produced in extreme environments such as supernova cores or near black holes, neutrinos carry information from the most violent processes in the universe. Facilities like the IceCube Neutrino Observatory in Antarctica have already detected high-energy neutrinos originating from distant galaxies, hinting at Andromeda's own potential as a source of such cosmic phenomena. Together, these advancements are transforming our understanding of the universe beyond the Milky Way. Each observation, each detection, and each theoretical breakthrough brings humanity closer to the moment when the Andromeda Protocol transitions from imagination to reality, a future where human presence is no longer limited by the boundaries of a single galaxy. If future detectors become even more sensitive, they could unveil dynamic activity in Andromeda's core that is currently concealed from view. As space-based technology advances, the ability to study Andromeda and other distant galaxies will continue to expand dramatically. Proposed missions such as the Habitable Worlds Observatory and the Large UV Optical Infrared Surveyor, LUVOIR, could offer unprecedented imaging power and deeper levels of observation. These next-generation observatories are expected to search for planets orbiting distant stars, investigate how galaxies evolve, and perhaps detect the first tangible signs of life beyond the Milky Way. One of the most enduring mysteries surrounding Andromeda lies in its dark matter distribution. Like the Milky Way, Andromeda is surrounded by an immense halo of invisible matter that shapes its motion and gravitational influence. Yet, studies of its satellite galaxies indicate that this dark matter halo may not be evenly spread. Some regions appear to contain more dark matter than others, challenging current cosmological models and suggesting that our understanding of dark matter's true nature may still be incomplete. Andromeda's spiral arms present another enigma. While it shares a similar spiral structure with the Milky Way, the behavior of its arms differs in subtle but significant ways. Some scientists propose that an ancient collision or close galactic encounter could have shaped these features, while others argue that they may have arisen from internal gravitational instabilities within the galactic disk itself. Observations from instruments such as the Hubble Space Telescope and the forthcoming Nancy Grace Roman Space Telescope may soon produce detailed maps of these arms, revealing how they have evolved over billions of years. Another striking mystery is Andromeda's unusually high number of globular clusters, dense spherical groups of ancient stars. The galaxy hosts more than 500 known clusters, more than twice the number found in the Milky Way. Researchers have debated their origins. Some believe they are remnants of dwarf galaxies that Andromeda absorbed long ago, while others suggest that Andromeda simply possesses a unique efficiency in forming such clusters. By studying their distribution and chemical composition, scientists hope to piece together the history of Andromeda's stellar population and its long record of galactic mergers. At the heart of Andromeda lies a puzzle of immense scale, its supermassive black hole. Despite Andromeda and the Milky Way being similar in overall size, Andromeda's central black hole is significantly larger. The reasons for this discrepancy remain uncertain. Did Andromeda's black hole grow rapidly during early cosmic history, or has it consumed surrounding matter at a higher rate over time? Future radio and X-ray observations may uncover the answer by tracking high-energy emissions and the behavior of material spiraling into the event horizon. Another open question concerns the relationship between Andromeda and the Milky Way. While their full collision is expected billions of years in the future, some astronomers suspect that their outer halos composed of gas, dust, and dark matter may already be overlapping. If true, the earlier stages of their merger could already be taking place. Upcoming observatories will be able to analyze the motion of intergalactic gas in exquisite detail, searching for telltale signs of early interaction that could confirm or refute this possibility. Recent evidence also points to Andromeda's complex star formation history. Data suggests that the galaxy has undergone multiple bursts of intense stellar activity, separated by long intervals of relative calm. Some models attribute these bursts to galactic collisions, while others point to internal processes regulating star birth. Mapping the ages and chemical signatures of stars across Andromeda, S, disk, and halo will help reconstruct the timeline of its evolution, offering clues to how galaxies grow and change across cosmic epochs. Galaxies themselves do not exist in isolation. They form part of a grand network of filaments, clusters, and cosmic voids, the large-scale structure of the universe. Astronomers believe that both the Milky Way and Andromeda belong to a flattened arrangement of galaxies known as the local sheet, which stretches across millions of light years. Studying Andromeda's position and motion within this vast structure could reveal new insights into how galaxies interact and migrate through the cosmic web. Some researchers also question whether our current theories of gravity are sufficient to explain Andromeda's motion. Alternative models, such as modified Newtonian dynamics, MOND, attempt to describe galactic behavior without invoking dark matter. If observations of Andromeda's rotation and mass distribution reveal inconsistencies with accepted physics, it could force a re-evaluation of fundamental gravitational laws, potentially reshaping our understanding of the cosmos itself. Part 11. Alien Architectures. Megastructures in the Andromeda Galaxy. If an advanced civilization exists within Andromeda, its technological footprint could, in theory, be visible even across the vast gulf of intergalactic space. The concept of megastructures, immense artificial constructions built on a scale far exceeding human capability, has become one of the most captivating ideas in the search for extraterrestrial intelligence. Such colossal projects could alter entire star systems, redirect stellar energy, or even manipulate space-time itself. Although no confirmed evidence of such structures has been found, astronomers continue to observe Andromeda with this possibility in mind, searching for any subtle signatures of engineered design. Among the most famous theoretical constructs is the Dyson sphere, proposed by physicist Freeman Dyson. This concept envisions a civilization enclosing its host star within an array of energy collectors, capturing nearly all of its radiant output. Variations such as Dyson swarms or Dyson rings imagine fleets of smaller satellites orbiting the star instead of a single continuous shell. If such structures exist in Andromeda, they might be detectable as stars that appear unusually dim in visible light, yet emit excess infrared radiation, the result of waste heat produced by massive energy collection systems. Infrared surveys conducted by observatories like NASA's WISE telescope have already scanned millions of stars within Andromeda, searching for these anomalies. While no definitive evidence of a Dyson structure has emerged, researchers emphasize that future instruments with higher sensitivity could eventually detect such phenomena. The discovery of even one would represent proof of technology far beyond human achievement, perhaps evidence of a civilization millions of years older than our own. Beyond Dyson spheres, other forms of megastructures have been proposed, each serving unique functions. One is the stellar engine, a hypothetical construct capable of moving entire stars by channeling their energy output in a single direction. A specific design, known as the Shkadov thruster, would use a massive reflective mirror to direct stellar radiation asymmetrically, gradually propelling the star and any orbiting planets through space. The presence of such a system in Andromeda could reveal itself through the unnatural drift of a star whose motion defies gravitational expectations. Another extraordinary idea is the ring world, a structure encircling a star at roughly the same distance as a habitable planet's orbit. Unlike a Dyson sphere, a ring world would not fully enclose its star, but would instead provide an immense, continuous surface along its inner edge, capable of supporting entire ecosystems. If a ring world or similar artificial construct existed in Andromeda, it might produce unusual transit signatures or light fluctuations distinguishable from natural planetary orbits. The possibility of such alien architectures remains speculative, yet their potential discovery would redefine humanity's understanding of life and intelligence in the universe. Even the faintest evidence of artificial engineering in Andromeda would signify that civilization is not a phenomenon confined to a single world, but a cosmic force capable of shaping galaxies themselves. If future instruments gain greater sensitivity, they may uncover hidden activity within Andromeda's core phenomena currently obscured from even our most powerful telescopes. As space observatories continue to evolve, humanity's window into the universe widens, granting us the means to explore Andromeda and other faraway galaxies with greater depth than ever before. Proposed missions such as the Habitable Worlds Observatory and the Large UV Optical Infrared Surveyor, LUVOIR, promise to reveal even sharper imagery and more profound data. These next-generation telescopes will search for planets circling distant stars, investigate how galaxies form and evolve, and hunt for potential signs of life beyond the Milky Way. Yet, as technology advances, so do the mysteries. One of the most compelling questions concerns Andromeda's dark matter distribution. Much like our own galaxy, Andromeda is enveloped in a massive, invisible halo of dark matter, yet observations of its satellite galaxies suggest this halo may not be as symmetrical as theory predicts. Certain regions appear to contain denser concentrations of dark matter, while others seem unexpectedly sparse. This irregularity raises questions about how dark matter is structured and whether our current understanding of its nature might require revision. Andromeda's spiral arms offer another enigma. Though it shares a broad resemblance to the Milky Way, its spirals behave in noticeably different ways. Some researchers argue that these structures were sculpted by ancient galactic encounters, while others believe they arose through internal dynamics within Andromeda's vast disk. Upcoming missions such as the Nancy Grace Roman Space Telescope building upon Hubble's legacy aim to chart Andromeda's spiral arms in unprecedented detail, tracing their evolution across billions of years to determine what forces shaped them. The mystery deepens when we examine Andromeda's abundance of globular clusters. Astronomers have identified more than 500, over twice as many as those orbiting the Milky Way. The origins of this disparity remain uncertain. Some theories suggest these clusters are the remains of ancient dwarf galaxies long since absorbed by Andromeda, while others propose the galaxy has simply been exceptionally efficient at forming them. By studying their chemical composition and spatial distribution, scientists hope to uncover the story of Andromeda's stellar assembly and the processes that built its population over cosmic time. At the heart of Andromeda lies yet another puzzle: its supermassive black hole. Remarkably, it outweighs the Milky Way's central black hole by a significant margin, even though the two galaxies are comparable in size. How Andromeda's black hole grew to such enormous proportions remains unknown. Researchers suspect that its presence has had profound effects on the surrounding environment, influencing star formation and the dynamics of its inner core. Upcoming radio and X-ray observatories may finally reveal the secrets of this immense object, observing the material spiraling inward and the powerful radiation it releases. A further question lingers: has Andromeda already begun to interact with the Milky Way? Though a full collision will not occur for several billion years, some astronomers propose that the outer halos of both galaxies composed of gas and dark matter are already overlapping. If this is true, the first phase of their eventual merger may have already begun in the shadows. Future telescopes capable of tracking intergalactic gas motions will help determine whether these subtle interactions are real, marking the earliest chapter of an event that will one day reshape both galaxies. Evidence also suggests Andromeda's history has been punctuated by bursts of star formation, alternating with long periods of relative calm. These episodes may have been triggered by earlier galactic encounters or by cyclical processes within Andromeda's disk. By mapping the ages, compositions, and movements of its stars across different regions, astronomers aim to construct a detailed chronology of the galaxy's evolution from its chaotic beginnings to the stable giant we observe today. Galaxies, however, do not exist in isolation. They are part of a grand cosmic framework composed of filaments, clusters, and vast voids that stretch across the observable universe. Both the Milky Way and Andromeda are thought to reside within a flattened structure known as the local sheet, a plane of galaxies extending millions of light years. Studying Andromeda's position and motion within this broader structure may illuminate how galaxies interact with their cosmic environment and how such vast networks influence their development over time. Some researchers even question whether our understanding of gravity itself is complete. By examining Andromeda's rotation curve and the distribution of its visible mass, astronomers test alternative theories like modified Newtonian dynamics, which attempt to explain galactic motion without invoking dark matter. Should Andromeda's behavior deviate from established models, it could prompt a profound rethinking of the fundamental laws that govern the cosmos. The image of colliding galaxies often evokes scenes of destruction, stars hurled from their orbits, planetary systems torn apart, and gravitational tides warping space itself. Yet within that apparent chaos lies creation. When Andromeda and the Milky Way eventually collide, their meeting will not only dismantle old structures, it will also ignite new realms of possibility. The immense forces unleashed will compress vast clouds of gas and dust, triggering spectacular starburst events that give birth to countless new stars. Around many of these will form swirling disks of material, the seeds of new planetary systems. Within some of these worlds, conditions could arise that allow life to emerge anew. In others, existing planets might endure the upheaval, altered but still potentially habitable. If life already thrives in either galaxy, it may adapt to these changing conditions, surviving within protected environments or evolving to suit its transformed world. Newly formed planetary systems in the aftermath of a merger will face harsh surroundings. Intense radiation from young, hot stars and powerful stellar winds will dominate these regions. Yet even such extremes need not exclude life. On Earth, microorganisms survive within boiling vents, frozen wastelands, and radioactive terrain, demonstrating that resilience may be a universal trait. Planets with thick atmospheres, subsurface oceans, or underground refuges could shelter simple life forms long enough to flourish despite the turmoil. The gravitational turbulence of the merger will also cast entire planets adrift, rogue worlds hurled into interstellar space. Though starless, these wanderers might retain internal heat from radioactive decay or tidal friction. If blanketed by dense atmospheres or layers of insulating ice, they could maintain subsurface oceans, perhaps sustaining microbial life in perpetual darkness. The collision will scatter dust, gas, and organic compounds, the molecular ingredients of life, throughout the newly merging galaxy. These materials, rich in amino acids and complex hydrocarbons, could seed forming planets and moons, spreading the potential for biology on a galactic scale. Some scientists suggest that life on Earth may have originated through a similar process, carried here by comets or asteroids. A galactic merger could amplify that mechanism across millions of worlds. Today, our Milky Way contains a region known as the galactic habitable zone, a band where conditions are neither too violent nor too barren for life. After the merger, This zone will likely shift as new stars ignite and old systems migrate. Regions once hostile may calm and stabilize, becoming new cradles of life. Conversely, areas that were once serene may be thrust into chaos. Some star systems will survive the collision relatively unscathed, continuing their orbits with little change. Should any of these harbor life before the merger, it might persist through the transformation. Intelligent civilizations, if they exist, would face immense challenges, but also new horizons, access to uncharted regions, opportunities for expansion, and perhaps encounters with other forms of life emerging in parallel. In this grand cosmic dance, destruction and creation are inseparable. As the Milky Way and Andromeda fuse, they will forge new stars, scatter old ones, and rearrange the architecture of space itself. Yet through this upheaval, the potential for life will endure, perhaps even flourish. Whether it arises anew on young worlds, survives hidden in ancient refuges, or journeys across the void aboard fragments of shattered planets, the story of life within the newly born galaxy will continue. The galaxy that emerges from their union will be one defined by change, adaptation, and renewal, a testament to the universe's endless cycle of death and rebirth. And with that reflection on creation born from cosmic destruction, our journey through Andromeda comes to a close, a reminder that even in the vastest reaches of space, the story of life and light never truly ends.